Hello everyone, I'm Manas from Another Coder, and in this video we're going to talk about Sieve of Eratosthenes. So first we are going to discuss why do we need Sieve of Eratosthenes, and then we are going to have a look at how does it work, and then we'll finally have a look at the code. So let me first tell you why do we need Sieve of Eratosthenes. So in the previous video we've already discovered the primality test, we know how it works and we know its worst case complexity. So the time complexity for the primality test is O of square root of n. So this is a pretty effective algorithm, but if we need like to find if a number is prime or not for a huge data set, then this particular method can pose a huge problem. For example, if you have 10 raised to the power 8 queries, and in each query n can be up to 10 raised to the power 4, then the total number of operations required to answer all the queries would be 10 raised to the power 10 operations. And how do we get this number? We just multiply the number of queries into square root of n. For example, here the n is equals to 10 raised to the power 4. So we multiply 10 raised to the power 8 with 10 raised to the power 2. So the total number of operations required will be 10 raised to the power 10. So this particular number is not desired. So we need to find an alternative method to answer all these 10 raised to the power 8 queries. So this is where we need sieve of Eratosthenes, and the pre-processing time for sieve is O of n log n. So what is this pre-processing time? So in sieve of Eratosthenes, what do? We maintain a Boolean array or a Boolean vector of numbers where we store for each number whether it is prime or not. So we calculate beforehand for all the numbers in the range from 1 to n whether they are prime or not, and then we can answer each query in constant time. We just need to look at the value at that particular index. If it is true, then it is prime. If it is not true, then it is not prime. So the time complexity to answer each query would be constant, and it will be done in O of 1 time. Now the extra space used will obviously would be O of n, because we are maintaining an array or a vector of n numbers, right? So now I'll tell you how this particular method of finding whether a number is prime or not works. So we have maintained an array. So this is actually a single dimension array. There was no space to represent it linearly, so I have done it in this way. This is not a multi-dimensional array, I repeat. This is just a single dimension array, right? So this is a Boolean array, and each element and each at each index we can either store true and false. So I have represented it with colors. For example, green color means it is prime, and yellow color means it is a composite number. So initially we assume that all the numbers present are prime, and we just mark 1 as a composite number, right? So we need to start traversing the array from the second position, because we know that 1 is already composite. So we start from the second position and we check for prime numbers. So for example, 2 in this position is prime. So what do? We mark all the multiples of 2 as composite numbers. So in this case, the multiples of 2 would be 4, 6, 8, 10, and all the even numbers would be the multiples of 2. So we mark all of them as composite numbers, right? So here you can see that these all are marked as composite numbers. Now we move further, and the next prime number is 3, right? So we stop at 3 and we mark all the multiples of 3 as composite. Again, the multiples of 3 would be like 9 and 15, and 18 is already marked, and 21. So these all numbers would be marked as composite. So now again we have marked the multiples of 3 is composite. So we move on further. We check for 4. Now 4 is already a composite number, so we don't need to do anything, because all the multiples of 4 are already covered. So we don't need to do anything for it. Now we move on to the next prime number, which is 5. So what do? Again, we mark all the multiples of 5 as non-prime or composite. So the multiples of 5 which are not marked are like 25 and 35, right? So we mark these numbers as composite. So now again the same process goes on, and we move on to 7, because 6 is already composite. We move on to 7, which is the next prime number, and we mark all the multiples of 7 as composite. So the only multiple remaining is 49, which is a multiple of 7, and it is marked as prime right now. So we mark this also as composite. So we have marked all the numbers in the range 1 to 50 as either prime or composite, right? So there's this one pattern that you must have observed till now, that when we start marking, we start from n square. For example, if I was marking the multiples of 7, I'll start from 7 square, which is 49. Why is it so? Because all the multiples of 7 starting from 2 to 6 are already marked, right? Because we have covered 2 into 7, we have covered 3 into 7, we have covered 5 into 7. So we need to start from 7 into 7 because all these multiples are already covered. So we need to start from I square, that is 7 square or 49. This is true for every number, and in this way we can mark all the numbers in the given range as prime or composite. So this is a very simple method of telling whether these numbers are prime or composite, and this works in n log n time. So now let us have a look at the code and how the code works. So we just create an integer n, which is the maximum number that can be given as an input, and we have to find whether that number is prime or not. So we create a boolean vector of size n plus 1. This is just for one based indexing, that's why we have taken n plus 1 size, and we mark all of them as prime. So in the starting we mark 0 and 1 as non-prime, we mark them as false, so that they are non-prime numbers, right? Now we start a for loop from starting from 2, and we go up to square root of n. Now this thing we have already discussed in the previous video, why we only go up to square root of n, because for every number n there exists at least one prime divisor till root of n. So this is what we are doing. We are doing I square is less than equal to n, or I is less than equal to root n. Both of the things mean the same, right? So this is the first loop, and we check if the number at I is prime. So if it is prime, then only we'll move further and we'll mark all the multiples of that number I as non-prime. So we start a loop from j, and j is I into I. As I've already told you why this is I into I, because all the numbers of I, all the multiples of I less than I are already covered. For example, I into I minus 1 is already covered, I into I minus 2 is already covered in the previous traversals. So now we just need to start from I into I, and then we go up to less than or equal to n, and we are just incrementing j by I. So we go from I into I, then I into I plus 1, then I into I plus 2, and this thing like goes on till we reach up to n, and we mark all these multiples as false. So false means that they are composite numbers. So now if we need to find like a number n is prime or not, we just need to check if it is like its value is true, then it is prime. If it is false, then it is not prime or composite. So this is the whole concept of Sieve of Eratosthenes, and like there's nothing more to it. But if you like want a mathematical proof of why this particular thing works in O of n log n time, then this is the analysis of the algorithm, and here they prove that this works in O of n log n time, right? And this can be found on the CP algorithms website. I'll leave a link to this page in the description, so that if you want, this is not very important to study, like, but if you want to like just do it for your interest or curiosity, then you can read this particular page. And there are different optimizations to the sieve also, like for example this particular optimization where we find for only odd numbers. So what this particular thing says is that we know that every even number except 2 are composite. So we don't need to check at all for even numbers, we can just check for all the odd numbers. So how this helps us, this will like we can make an array of half the size of the original array just for the odd numbers. So this time we only need to create half the size of the array, and also the number of operations in our algorithm would be reduced in half. Like, so these are the small optimizations that you can make to the sieve. And I guess this some extra things as well, such as segmented sieve. Like topics like segmented sieve we'll discuss in further videos. I will tell you how this particular thing works, but for now that's it for today. And I hope you guys enjoyed this particular video. If you did, please drop a like. If you like love the content, please do subscribe to this channel, and we'll meet in the next video. Till then, stay safe, keep coding. Bye bye.